Hello and welcome to this video on determining whether a vector is in the column space of a matrix. So in this video I'm going to start off by defining what the column space of a matrix is, right? A general M by N matrix with real entries. Then we'll go into the heart of the title of the video. Once we know what the column space of a matrix is, we'll then see if a given vector, we'll have to determine whether or not that given vector is in the column space of some given matrix. And hopefully what you're going to notice here today is that this video is very similar, almost exactly the same as another video I put out, again if you've been following, in which I determine whether a vector is in the span of another set of vectors. You're going to see it's exactly the same as that concept there. All right. So this first page I define what is this column space I speak of, right? The column space of a matrix. All right, so suppose we're given a matrix A that is an M by M matrix, right? So M rows, N columns. And I structure it like this. A equals, it's got the matrix brackets, and then these column vectors, right? Notice I call these column vectors, so these are column 1, column 2, column 3, column 4, all the way up to column N, right? It's got N columns. And each of these N columns has, our M as in mom, component vectors. So that makes up the M rows and the N columns. Where, again, I say here A1, A2, all the way up to AN. You see how they belong to RM, right? So they each have M components, making up, giving me those M rows. And these are called the column vectors of the matrix. All right, so the column space of matrix A, denoted by this cola, right? It's column space of A in parentheses. The column space of A is the subspace of Rm, right? Like each of the columns from the matrix comes from Rm, right? As a vector from Rm, right? Euclidean space, and it's the subspace, right, of Rm spanned by the column vectors of A, right? So if you remember span, I can write it this way. The column space of A is the span of the n column vectors, right, of A. And remember how, again, a while back on the span video, the span of a set of vectors is going to be a vector space, right? So that's what I'm saying here. It's a subspace of Rm. The span of a set of vectors will satisfy all 10 of the vector space axioms. And if you don't remember what the span of a set of vectors is, I'll re-describe it here. The span of a set of vectors was the set of all linear combinations of those vectors. So another way I could write this is that the column space of A is, again, the set of all linear combinations, x1 times A vector, the column vector A1 plus x2 times the column vector A2 plus all the way up to x, that's an x, sorry, it's a little thick there, xn times column vector an, where this x1, x2, all the way to xn here are scalars, right? They belong to some field, but typically we're just going to have that field be the real numbers. So x1, x2, all these coefficients of the column vectors are scalars, they belong to the real numbers. All right, so in order for a vector to belong to the column space, it just has to be a linear combination of the column vectors of the matrix. All right, so I wrote that here. So in order for a vector, say B, right, a little arrow above it, vector, which would belong to Rm, right, have M components, in order for a vector B to belong to the column space of m by m matrix A, B must be a linear combination of the column vectors of matrix A, right? Of the columns of matrix A. So this equation, they take a linear combination of the vectors, the columns of A, x1 times a1 plus x2 times a2 plus, all the way up to xn times a, must be equal to B. This must have a solution. All right, this equation must have a solution, at least one. All right. And again, these are the solution of this equation would be the values of the scalars, the weights of the linear combination, right? x1 through xn, that values of those that satisfy the equation. Now, another way to say this, this equation here, right? When you have a linear combination of vectors equal to another vector, that can be written as a matrix equation as well, right? Or just an augmented matrix. It corresponds to a system of equations, which you've seen plenty of times before by now, hopefully. So I can write this linear combination of vectors as the matrix A itself multiplied by a variable matrix, a vector x, where this vector x is from Rn, and the vector x it just consists of all the weights, right? All the values of the scalars x1 through xn as their components. So I have matrix A times the weights, right, times the values of the x's, equal to the matrix, the vector, the column vector B. So this, or this must have a solution. Right, there must be a values of these x's that I can replace to make this a true statement. In order for us to be able to say that vector B belongs to the column space of vector A, right, or of matrix A. In other words, B belongs to the span of the columns of A. Right, that's all the column space is. It's just the span of the columns of the matrix. All right, so just a new word for an old idea now, right? It's just related to matrices. You've seen in past videos and past, probably sections you've been reading or working on. Hopefully, you know what the span of a set of vectors is. So this concept here of column space is really no different from that. All right, so let's do this. So we're going to set up equations like this and solve and all that good stuff. And again, it's all going to boil down to solving a system of equations, some matrix equation, right? Things you're most likely familiar with at this point. All right, so for the rest of the video, I have the following instructions, right? Every example I have for the rest of the video has the following instructions. Determine whether vector B is in the column space of matrix A. Remember that's denoted this col of A, column space of A. All right. Now I'll write out here, I'll describe to you before I get into determining this, what the column space of A is. So here the matrix A is this 3 by 3 matrix, right? It's a 3 by 3 matrix. So the columns belong to R3. You see that? All the columns of matrix A have 3 components. So the column space of A, right, is just it's the span of this set of vectors, the set with the vectors 1, 2, 3, and the vector 0, 1, 2, and the vector -1, 0, 1, right? All the columns of matrix A, right? Or, as I was writing on the previous page, you could think of the column space of this matrix as, what is the span of a set of vectors? It's the set of all linear combinations. So all x1 times 1, 2, 3 plus x2 times 0, 1, 2 plus x3 times negative 101 such that, you know, x1, x2, and x3 are scalars, right? We have, you know, just every linear combination of these three vectors, the column vectors, make up what's called the column space of A. And one other note to make here is that, you know, all these vectors in the column space of A are, you know, three component vectors. This is a subspace of R3. Something else to point out, right? Now, it doesn't mean that it is R3, right? It could be. You know, the entirety of R3 is a subspace of R3, but it could also be one of those subspaces of R3 that's just a plane containing the origin, or just a line containing the origin, right? One of those subspaces. It's obviously not, you know, that subspace which just has the zero vector in it, because, you know, I mean, this would have the zero vector in it, but the zero vector is not the only vector in it. But just know that when you're looking at the column space of a matrix, it is a subspace of some Euclidean space. Okay. All right. So now the question is, you know, does B belong to the column space of A, right? Does matrix, vector B here, this 1, 1, 1, belong to the column space of A? Right, well, that's the same thing as asking, sorry, that's an A. That's the same thing as asking, is B in the span of these three vectors? Or can B be written as a linear combination of these three vectors? Right, so as I mentioned on the last page, in order for this, you know, to determine whether or not B belongs to the column space of A, we're looking at this equation. We're going to ask, can we find x1, x2, x3 such that, you know, a linear combination of these three column vectors is equal to B, such that x1 times 1, 2, 3 plus x2 times 0, 1, 2 plus x3 times negative 1, 0, 1 is equal to B, right? And B is this 1, 1, 1 up here. Well, you've seen this, hopefully by now, by the time you get to this concept of column space of a matrix, hopefully you've seen solving equations of this nature several times before. Remember, this corresponds to a matrix equation. If you want to write it as a matrix equation and also as an augmented matrix for a system, I could re-express this as, you know, the matrix A, right? This 1, 2, 3, or the coefficients of x1 down the first column, you know, the coefficients of x2, just this vector, down the second column, coefficients of x3, just this vector, down the third column. There's A times, and then that vector x, which is made up of the scalars x1, x2, x3, right? The variable matrix, right? And in the correct order, right? Just make sure whatever order you put the columns in, that's the order you're putting the variables in. And this needs to be equal to, you know, 1, 1, 1, right? Matrix vector B. And again, does this have a solution? And this is a question here. You know, can we find that? Can we find? So question mark. So we're trying to solve this. Now, if you wanted to, right, you could see, you know, check to see if, now this is a square matrix, right? It's 3 by 3. So if you wanted to, you could see, hey, you know, does this have an inverse? You know, try to find that. But I'm going to go to the, because not every system we're going to see is going to be a square system, have a square coefficient matrix. I'm just going to stick to my favorite method, is just putting it in as an augmented matrix, and, you know, putting it in reduced row echelon form or just echelon form. One of those two in solving. So here's the augmented matrix for this system. You know, coefficients of x1 coefficients of x2, coefficients of x3, and the equals sign, a little bar, and then vector b on the other side, right? All right. And then now you could do it by hand, all right? We could do this by hand where I use row operations, Gauss-Jordan elimination to put this in reduced echelon form. But I am going to skip ahead here and let the calculator do it for me. All right, so I'm going to go to reduced echelon form, or what's called reduced row echelon form very often, RREF, in our calculator here. Now I have a TI-84 plus, similar to an 83 as well. So I go to the matrix menu, over to edit. This is when I look at the augmented matrix here, this is a 3-row, 4-column matrix, so size is 3 by 4. Enter the first row, 1, 0, negative 1, 1, then 2, 1, 0, 1, and 3, 2, 1, 1. Alright, then I get out of here, quit, and I want to have the calculator put it into reduced row echelon form for me. Go back to the matrix, over to math, scroll up until I see RREF. Again, don't confuse this with REF. That's just row echelon form, or plain old echelon form, where the zeros need to be just below, just below the leading ones, just below the pivots. Whereas in, remember, reduced, the zeros need to be below and above the pivots. So I prefer that. Right, so reduced row echelon form, and then back to the matrix. Matrix A is the one I want to put in that form. And here we go. All right, so here it is. We have first column 1, 0, 0, second column 0, 1, 0, negative 1, 2, 0, little bar, and then 1, negative 1, 0. All right. So, looking at this matrix here, the last row is fine, right? The last row tells me, that 0x1 plus 0x2 plus 0x3, so 0 equals 0. And 0 equals 0 is a true statement. There's nothing wrong with that. I can continue, all right? So this system will actually have, this equation actually has infinitely many solutions. So it has at least one solution. And let me show you. Let me just try to find one of these. Now remember, look at when you put this augmented matrix into reduced row echelon form, right? You look for your pivots, where those leading ones are for the rows, right? There's a leading one. So there's a pivot here, so x1, right? This was the coefficients of x1. x1 is what they call a basic variable. Same thing here, there's a pivot, a lead 1 in the second column. These were coefficients of x2, so x2, also a basic variable. And notice that in this third column, there are no leading ones. All right. So x3 is not a pivot column, doesn't have a pivot in it, this column here. So x3 is what they call a free variable, meaning I could replace x3 with any number I want, right? Any real number I wish. But then once I do, the values of x1 and x2 will be determined, right? I can't replace x1. Once I replace x3 with some number, I couldn't then go and replace x1 and x2 with anything I wanted, right? They'd have to be determined, they'd be fixed, all right? Now, something I like to do with all my free variables, now you can leave it as x3 if you wish, but I like to replace the names of the variables with other parameters. So I'm going to replace x3 with the letter, now usually it's the letter T, it doesn't have to be, right? S, T, R, Q, whatever you want, 5T, T plus 1. You can replace your free variables with any expression that can take on any real number value, right? Where T can be any real number, can it? All right. And so can x3. Right? I just want to make sure that I replace it with an expression that can take on any real number value. All right, so then doing this, let's see what the first row tells us, right? The first row is saying that we have x1, right? 1x1, the basic variable, plus no x2, minus 1x3. So minus x3, that's minus this t that I'm calling it, must be equal to 1, right? And then I go and solve this for x1. I get x1 in terms of the free variable t. x1 must be, 1 plus t. 1 plus t for whatever my choice of t is. Then the second row tells me that I have 1x2, so x2, plus 2x3, so plus 2 of this t, must be equal to negative 1. And solving this for x2, right, getting x2 in terms of the free variable t, we have x2 equals, negative 1 minus 2t. All right. So the solutions of this equation here, right, the solution of this system, look like this. x1 is, 1 plus whatever I choose for t. The value of x2 is negative 1 minus 2 times whatever I choose for t. And the value of x3 is, whatever I choose for t. Right, now this isn't the answer, right? The question is simply, does 1, 1, 1 belong to the column space of matrix A, right? Is it in the span of those column vectors? Well, clearly it is, right? There are infinitely many solutions here, all right? This is telling me that there are infinitely many solutions to this equation I wrote up here, right? Or this system here, this matrix equation. This has infinitely many solutions. So, because the system has solutions, right, because the system does have at least one solution, this tells me that B, right, that vector 1, 1, 1 does belong to the column space of matrix A. So yes, it's good, right? Now, sometimes you might be asked, well, hey, if it's actually in the column space of a matrix, right? If this vector is in this column space, can you show me how can I write this vector as a linear combination of those columns? Or that's where the solutions come in. So what I'm going to do here is I'm going to replace. So take this here. Let's let t be, and you can have t be anything you want. If t were 0, the value of x1 would be 1. The value of x2 would be negative 1, and the value of x3 would be 0. And we'd get the following, right? If I go back up to the equation here with the linear combination, we'd get the following. We'd see that 1, 2, 3, right? That first column from matrix A. Then, that's replacing x1 with 1, replacing x2 with negative 1. It could be minus, and then 0, 1, 2, that second column from matrix A, and then plus 0. So I don't really need to do that. When you have 0 of a vector, you have none of it. That'll be equal to 1, 1, 1. That's one way you can see how 1, 1, 1 is in the column space. Right? And do you see how, like, you don't really need this vector, right? I showed you how this is actually in the span of these two. But we'll get to more of that when we talk about the basis for a column space in the next video. But yeah, let's check it out. 1 minus 0 is 1, 2 minus 1 is 1, 3 minus 2 is 1. Hooray. It works, right? But you could have done that with any value of t, though, right? But as long as you find one solution. All right, so let's say let's take the solutions again here, and say let's let t be equal to 4, whatever you want. In that case, x1 would be 1 plus 4, right, 5. x2 be negative 1 minus 8, right, 2 times 4, so negative 9. And then x3 would be 4. And let's see the linear combination that comes out of that. Right. So again, back to the equation. All right, here's that equation where I'm filling in x1, x2, x3. Now you could fill it in here as well and see that this matrix equation is true. I'm just going to go back to the linear combination equation. So I replace x1 with 5, so we have 5 of that first column from A, and then replace x2 with negative 9, so minus 9 of the second column from A, that's 0, 1, 2. And then x3 is 4 plus 4 of that third column from A, negative 1, 0, 1. This should be equal to B as well, right? Equal to 1, 1, 1. And let's see, you'd have in the first components, you'd have 5 plus nothing, and then minus 4 would be 1. Great. And then the second component's 10 minus 9 is 1 plus 0 is 1. And the third component's 15 minus 18 is negative 3, and then plus 4 would be 1. It also works, right? But again, you don't have to go through and find a bunch of examples. If you can find just one example where this vector b can be written as a linear combination of the columns of A, then vector b is in the column space of A. Okay. All right, so what I'm going to do from here on out is kind of just like, maybe for the next example I'll just write this one more time, but then after that I'm just going to kind of jump to the augmented matrix and put it in reduced echelon form, because you should hopefully after a while here recognize how to construct this augmented matrix, right, where you see that these are just the columns of A, right, the columns of matrix A, and then to the right side of the equal sign, the right side of the bar, that's just the vector b that I'm trying to see if this is in the column space of this matrix. So yeah, I'll do one more lawn version of an example, and then we'll do shortcuts. Right, just write the augmented matrix after. All right, so this matrix, this next example, I have the same. This is the same matrix as I just had. All right, so same column vectors: 1, 2, 3, 0, 1, 2, negative 1, 0, 1. But this time I have a different vector b. Right. All right, so I'm not going to write the column space of this again. I did that with the last example. The column space of A is just all linear combinations of these three vectors. And the question is again, is B, does B belong to the column space of A? Right. So the last example with 1, 1, 1, it did. All right. So what we're trying to do is find solutions to this equation, right? Can I find an x1 multiplied by the first vector, the first column of A, plus an x2 times the second column of A, plus an x3 times the third column of A. Can I find this x1, x2? Can I find an x1, x2, and x3 that'll give me this vector b here? All right, so 1, negative 2, 2. And again, you can write this, if you would like, as a matrix equation where you have matrix A basically. Again, the coefficients of x1 would be down that first column, that first vector. Coefficients of x2, or that second vector down the second column. Coefficients of x3, or the third vector down that third column. Multiplied by the variable matrix, which are just the values of the scalars, right? x1, x2, x3, the weights of the linear combination. And when is this equal to, the vector b? But as I said before, I'm just going to, in the future examples from here on out, I'm just going to write it as its augmented matrix. Coefficients of x1, coefficients of x2, coefficients of x3, a little bar where the equal signs would be, and then 1, negative 2, 2, right? So again, here I have basically just matrix A, right? Matrix A here, and then over here vector B, right? And then I put this into a reduced row echelon form, and with the calculator. And you know, this matrix A, right? The 3 by 3 over here. This is the same as the last example. So when I go to the calculator, the only thing I'm going to need to change is vector B. Right? It was 1, 1, 1 last example. Now it's 1, negative 2, 2. So back in the matrix menu, over to edit. Matrix A again, 3 by 4 still. Right? It's still a 3 by 4. Again, all this stuff here is the same. Right? These 3 columns are the same as the last example. It's only this last column with 1, then negative 2, and then 2. Right? That's the only thing I need to change. And then the last thing I entered was, you know, reduce row echelon form for matrix A, so I'll re-enter it, the second enter. Right, and there we go. And look at this matrix here, right? You got this. Notice that the first 3 columns are looking exactly the same, you know, because it's just putting matrix A into reduced row echelon form. So no matter what I put on the right side of the bar, this left side of the bar will always look the same when I put it in reduced echelon form. So it's still the same as last example, you know, 1, 0, 0, 0, 1, 0, negative 1, 2, 0. The thing that changes is, you know, the other side of the bar, because I actually changed it. Right? It's not 1, 1, 1 anymore. That's now 0, 0, 1. All right, and now look at that last row now. You have no x1 plus no x2 plus no x3. That's 0 equals 1. Uh-oh. Right. That is always a false statement. That is no good. Right? There's nothing you can do to fix that. And that implies to me that this system is inconsistent, right? This equation has no solution. Right, so this tells me that the equation has no solution. So, unlike last example, B here, right, this vector 1, negative 2, 2, does not belong, right, a little slash through that, does not belong to the column space of A. So that would also tell me, right, that the column space of A isn't R3, right? I said that last one. The column space of A isn't R3 because there are some vectors in R3 that aren't in it, right? So that set so these column vectors also, you know, you could say that the set of column vectors, these 3, do not span R3. Right, because again, there are vectors in R3, like this 1, negative 2, 2, that can't be written as a linear combination of these 3 vectors. And you probably figured that out already because remember when we take if you want to figure out if a bunch of column vectors span a space, right, span an entire space like R3, R4, or whatever, when you put it in reduced row echelon form, if there was an entire row of zeros like there is here, the 3 zeros down here, then there were some vectors that it wouldn't, you know, that wouldn't be in the there's some vectors in the larger space, the Euclidean space, that wouldn't be in the span of those vectors, right? So it didn't, you know, it wouldn't span R3. But enough of that, right? You've seen that before, hopefully. All right, so pretty easy to set up. Now from here on out, for the last few examples, I'm going to just take my matrix and my vector here, and you know, is this in the column space of this? Just going to jump and make the augmented matrix. Right. So here we have matrix A is, you know, columns 1, 3, negative 1, negative 3, which, you know, you can probably see that these are multiples of one another, and 2, 1. Right, it's a 2 by 3 matrix. Right, 2 rows, 3 columns. And each of the column vectors is from R2, right? Each of the columns has 2 components. And the question is, you know, is this other vector from R2, right, this negative 1, 7, is this in the column space of A? Alright, so I will again here describe the column space. Right. The column space of this matrix would be the span of the set with these three vectors. Right? 1, 3, -1, -3. Now you might be able to tell, hey, you don't really need that one, because it's just a multiple of this first one, a scalar multiple. But that's not the point right now. All right, my next video I'll talk about finding a basis for a spanning set, right? A basis for a column space, where we'll get into what vectors are really unnecessary to build the whole space. And another way you could write this too is again the set of all linear combinations. The scalar x1 times vector 1, 3 plus scalar x2 times vector -1, -3 plus scalar x3 times vector 2, 1. Right. Such that the x1, x2, and x3 I said already were scalars, and in this case the scalars are real numbers. All right, so a couple ways you can describe the column space of this matrix. And as I've said in the last examples, right, the column space of a matrix is a vector space, right? And it is these vectors here are from R2, so this is a subspace of R2, right? So it might be all of R2 itself, right? In fact, it would be, because this first vector and third vector here are independent. But again, like I said, we'll get into that in the next video on finding a basis for a column space. But this span of this set of vectors is a subspace of R2, so it's a vector space on its own. And so remember, it could be all of R2, or it could form a line going through the origin in R2, or it could just be, no, it's not just that subspace with just the zero vector in it, because obviously there's more than just a zero vector in this, but just know that it's a subspace of R2. Okay. So now the question is again, does this vector -1, 7 here belong to the column space of A, right? Is this vector able to be written as a linear combination of these three columns? Right. All right, so as I said before, I'm just going to skip ahead. I could say, hey, let's make a linear combination here, set it equal to this. You could write it as a matrix equation where you have this 2 by 3 matrix multiplied by the 3 by 1 variable matrix with x1, x2, x3 in it equal to -1, 7. But that would all correspond to having, I could have a corresponding augmented matrix here where again just the coefficients of x1, 1, 3. The coefficients of x2 would be that second vector -1, -3. The coefficients of x3 would be this third vector 2, 1. And an equal sign, and then vector b on the other side, we want this to be equal to -1, 7. All right. Okay, so this one wouldn't be terribly difficult to put in reduced echelon form by hand, right? So I'm going to reduce row echelon form. All right, so I'm just going to do something here where I just kind of scratch off stuff. I would multiply this first row by -3 and then add it to the second row, because there's a pivot, a lead one in the first row, upper left corner. And if I multiply that by -3, add it to this, that would make this 0. Same thing here, 0. All right, 3 plus -3. Then, -6 plus 1, that would make this -5. And then 3 plus 7 would make this 10. All right, and then I would say, okay, there's a lead 1, 0 is above and below it. This first non-zero entry is -5, not 1 for the second row. So I multiply everything by -1/5. And that would make this into 1 now. And multiplying this by -1/5 would make it -2. And then great, it's got a now it's got a lead 1, right? This pivot place, and then I need to get the 2 above it to be 0 to put it in reduced echelon form. So I multiply this by -2 to add it to this, make that a 0, and then multiply this by -2 also, make that 4, add it to this, which would make this a 3. and that's in reduced row echelon form. And you can double check on the calculator if you want, but 1, 0, negative 1, 0, 0, 1, and then 3, negative 2. Right, again, if you want, put in a 2 by 4 matrix, have it go into the reduced row echelon form in the calculator if you wish. All right. So, looks to me like there are solutions. All right, there are solutions. You know, look at the pivots. Right, first column's a pivot, so x1 is basic. Then the next pivot where the lead ones are is in the third column. All right, so x3 is another one of these basic variables. So x2 doesn't have one of these pivots, these leading ones in it. So x2 is a free variable. All right, so what I'm going to do is, like I like to do with free variables, I'm going to replace x2 with t again. I'm going to let x2 be equal to t, where t is, you know, any real number. I'll just say t belongs to the reals like I did last time. All right, so that first equation, now I already know, right? I already know that B does belong to the column space of A. All right, this has solutions, but let's get into it. I'll describe the solutions. So from the first row, I'm getting x1, all right, the basic variable, minus x2. So minus this t must be equal to 3. So x1 must be equal to 3 plus t, right? When you solve for the basic variables, you know, get them in terms of the free variables, which there's only one free variable here, this t. And then the second row is just simply x3 equals negative 2. Okay, and that's it. You could say it's negative 2 plus 0t if you wanted to write it in terms of the free variable, but you know, it's basic. It's going to take on the value of negative 2 no matter what. So this definitely has infinitely many solutions, this equation, right? So the solutions, right, x1 equals 3 plus t for, you know, whatever I choose for t. x2 was just t, and x3 is always negative 2. So definitely has solutions. That tells me that this vector, right, negative 1, 7, this vector does belong to the column space of that matrix, right? It can be written as a linear combination of the columns of A. And let's see how, right? Let's see how. So I'm just going to pick, now again, remember how earlier I was saying that, you know, you don't really need the negative 1, negative 3 because it's just a multiple of 1, 3. You know, any variable that is a free variable, you can get rid of the corresponding vector by just letting it take on the value of 0, right? To show you that that vector is really not needed, right? Because if I let t equal 0, right, you would then see that, you know, x1, the value of x1 would be 3, right? 3 plus 0. And you see how the value of x2 would just be 0, telling me that this second vector is not necessary. All right, so the span of these three vectors would be the same as the span of just 1, 3, and 2, 1, just those first and third vectors. And then x3, if t were 0, is always negative 2. Right? And let's see what linear combination we get out of this. So if I take, you know, 3 of that first vector, 3 times 1, 3, plus 0 of the second vector, so I'm not going to write that, and then minus 2 of that third vector, right? Minus 2 for x3 times 2, 1. Does that give me b? Does that give me negative 1, 7? Well, let's see. That's, you know, first components is 3, and then minus 4 is negative 1. Check. Second component is 9, minus 2 is 7. That works out. So definitely, negative 1, 7 is in the column space of A. And you could have replaced t with anything you wanted. Right? I just like replacing the free variables with 0 to show me, you know, what vectors aren't really necessary to span the space, right? And that's going to be very important again when we get into the next video on, you know, what's a basis for a spanning set, right? What's the basis for a column space of the column space of a matrix? All right, next example. Just got two more here. All right, so this time I'm not even going to write out the column space. You can imagine it, right? The A is this, it's a 3 by 2 matrix this time, 3 rows, 2 columns. So I'll just write this, right? I'm just going to write that the column space of A here is a subspace of R3. Right? It'll be a set of vectors from R3 that form a vector space on its own. Right? So it's a subspace of R3. I'll just at least write that, because the columns, look at the columns are, these are vectors from R3, right? They have 3 components. So any linear combination of these two is, you look at that span of those two, the column space, it'll form a vector space that is also a subset of R3. Great. Same question, right? Does vector B here belong to the column space of A? Now you could set up a x, I'm going to use x1 and x2 this time. X1 times this first vector plus x2 times this second vector. Can I find an x1 and x2 that will make that equal to this b here? All right. So again, you can write the equation, write the matrix equation. I'm just going to jump to one more. Like I said earlier, I'm going to jump to the augmented matrix for that equation. So negative down the coefficients of x1. All right, and I'll put like x1 up here just so you know that these are coefficients of some x1 that I'm looking for. That's that first column vector. And then the coefficients of x2, the second column vector. Then the little equals, and then the matrix, and then vector b over here, right? Negative 22, 4, 32. Right, so I have a 3 by 3 matrix, this augmented matrix. I have the calculator do this for me. I'm going to have it put it in reduced row echelon form or reduced echelon form. Alright, so back to the matrix menu, over to edit. This is a 3 by 3. First row, negative 3, 5, negative 22, 3, 4, 4, and then 4, negative 8, 32. Alright, and then last thing I entered was again reduced row echelon form for matrix A, so let's re-enter that. There we go. Alright, so we've got this matrix here. So 1, 0, 0, 0, 1, 0. Bar, right? That's where the bar would be after the second column, where the equal signs are, and then 4, negative 2, 0. Alright, so it looks like, again, look at that last row. We're fine, right? This is just saying 0x1 plus 0x2 equals 0. This is just 0 equals 0. That's golden. We're totally fine. Alright. And then this first line is simply saying x1 must be equal to 4. Second line saying x2 must be equal to negative 2. There is a solution, but there's not infinitely many like the last couple, like a couple of my examples prior to this. There's only one solution, but there still is a solution. Right? There still is a solution to this equation. So there is a linear combination of these two column vectors that would make vector b here. All right, so b, this negative 22, 4, 32, does belong to the column space of matrix A. And if you'd like to verify that, let's, again, this is the only thing I can check. I can't just plug in values for t or whatever. There's not infinitely many solutions. Let's take 4 of that first vector from matrix A, first column, and add to it, negative 2. So minus 2. Right, minus 2 of that second column, the 5, 4, negative 8, and see if we get vector b here, the negative 22, 4, 32. Alright, let's see. First components, you have negative 12 minus 10, that'd be negative 22, yeah. Second components, 12 minus 8 is 4, great. third component 16 plus 16 is 32. Wonderful, it works out. So this vector can be written as a linear combination of these two columns, and here's how. Right. It is in the column space. All right, finally, one last example here. So again, here I have a 3 by 4 matrix A, and I'll make that note again. Now look at every column, right? Every column is a vector from R3, right? It has 3 components again. So the column space of A is a subspace of R3. Okay. So if you looked at all linear combinations of these 4 vectors, right, these 4 column vectors, that span, right, the span of those 4 vectors, again, form a vector space, and that vector space is a subset of R3. So you have what's called a subspace of R3 again. Right? So same question, every problem here. Does this vector here, this -3, 15, 18, belong to the column space of this matrix? All right, so as before, as the last example, you could set up the equation where I have x1 times this vector plus x2 times this vector plus x3 times this vector plus x4 times this vector equal to this vector, and see if I can find x1, x2, x3, x4. Right? Set up the linear combination equation or the matrix equation. But I'm just going to write again the corresponding augmented matrix for that equation. So coefficients of x, again x1 down the first column, coefficients of x2, that second vector, down the second column, coefficients of x3, coefficients of x4, 10, 12, 29, and then equals, and then vector b over here, right, -3, 15, 18. And again, you can do it by hand if you wish, but I'm going to have the calculator do this again. Put this into reduced echelon form or reduced row echelon form. So this is a 3 by 5 matrix, this augmented matrix. Alright, so back to the matrix menu, over to edit. Alright, 3 by 5. First row 2, 2, 2, 10. Second, -3. Second row 0, 4, -12, 12, 15, and then 7, 5, 13, 29, and 18. Alright. So get out of here, reduce row echelon form again. And I'll write it, but you can hopefully see that the answer is no. Right, so 1, 0, 0, 0, 1, 0, 4, -3, 0, 2, 3, 0, bar, 0, 0, 1. Wonderful. All right, look at that last row. Uh-oh, right? You got no x1 plus no x2 plus no x3 plus no x4. 0 equals 1. That is always false. That is not a good statement, right? And you can't fix that anyway through reworking the problem. So this equation, this this system I set up, this equation has no solution. It's inconsistent. So the answer is no. Right? Vector b here, this -3, 15, 18. Does not belong to the column space of A. It cannot be written as a linear combination of these 4 vectors. Alright, so what that tells me too is that the set of these 4 vectors doesn't span R3. And again, you see this row of zeros when you put matrix A in reduced row echelon form, right? It doesn't span R3 because there are vectors in R3, as we've seen, that can't be written as a linear combination of those 4 vectors that aren't in the column space of that matrix. All right. So that's it. Okay. You see, it's very similar to that span video, right? Talking about whether, because asking if a vector is in the column space of a matrix is exactly the same as asking if a vector is in the span of a set of vectors. All right, so you go through the same procedure, set up the same kind of system, write the same kind of augmented matrix, solve it the same way. All right, so I hope you have fun practicing problems like this and enjoy learning. And thank you very much for watching.